What country fish come from?
Finland.
We've got our 8 BCers joining you guys today, just because it's been a basic lecture on volume. There you go. Get away.
Everyone just look at you going.
This debate's over. Not personal.
If I ask you to find the volume of this,
These are ideas.
you say, well, it's by r squared
I like it.
times the height. Volume of this, 1/3 the area of the base, whatever it is, 1/3 base times height there, times its height. Volume of this would be whatever the base volume is, or area is, times its height. 1/3 base times height. Okay. Volume of this. Not quite as easy. Volume of this. Not quite as easy. Why isn't it quite as easy? It's curves. But because they're not shapes that we have formulas for. So, what we're going to learn is finding volumes by slicing, by discs, by washers, and tin cans, although the authors in math books call it the shell method. Okay. All right. So in the first situation, I'll let you copy those. I'm going to take each one individually. So
That's Monday's quiz for 7.1 through 7.8.
I don't know, is that what I said?
It's on
I
Friday.
don't know, I won't be in school Monday.
This
It's on Friday.
This Friday.
Oh yeah, I won't be in school on Monday either.
I'm not going to be on Friday.
I'm not going to be the rest of the year.
Okay, here is, that's the wrong one. I don't have an example. Assuming this was square on the bottom, I could find the volume by 1/3 of the base times the height. Well, this is basically the same shape. The volume of this figure here is 1/3 the base times the height. However, what I've done is I've sliced it into squares and find the volume of each square and then just add up all these squares. So all you're doing is figuring the volume by slicing it into pieces that you know how to find the volume of. And of course, this is just, 20 squares or whatever. In calculus, we can integrate it and do an infinite number of pieces. So let's do the first example by slicing.
Maybe I should have wrote this down. Whatever.
Let's take a
I have a solution.
let's take a pyramid that's 4 by 4 and 4 feet high. Okay? Now, we do have a formula for this. The purpose of today's lecture is just to give you the methods. You wouldn't need to use calculus for this. You could just go 1/3 the base times the height, which would be what? 1/3 times 16 times 4, 64/3. Which is the answer we better get when we use the slicing method. All right. So what I'm going to do is just turn it on its side and let's see. And have it 4 by 4 and come out 4 feet. Okay? Can you visualize that? No? Now that's the base. So all I've done is take this thing here and turned it sideways.
So half of it is under the x-axis, right?
Yeah.
No.
And so I'm going to simply take this and put it into squares and slice it up. So I just got a bunch of slices here. Just a bunch of slices coming out. All right? So the volume equals the sum of slices. And what is the volume of each slice? The volume of each slice is the area times its thickness. So we're going to find the area of each slice and then multiply it by its thickness. All right, well, let's take a slice. If we come out a distance x, this is 4 all the way there, but if we come out a distance x, let's say to this slice here, that represents the length of the side and the height of the square. So whatever distance you go out, that's the size of the base. So the area would be x squared. And then what is its thickness? Well, the thickness is the direction that we're going in. We're going in an x direction, so the thickness is a dx, or a delta x, either one. So that's how much, that's the volume of each slice. It's x by x and has a thickness of dx. And then what are we going to do? We're going to add up all the slices that go from 0 to 4. So the total volume is simply the integral from 0 to 4, the area of the slice times dx. Okay? Now you just work it out. It would be 1/3 x to the third. It's evaluated at 4, and it's 0. Which would be 64/3. So essentially what you do is you slice the object and you find the volume of each slice. And of course you have to be able to find the volume of each slice to do the method. Yes?
So each slice being x squared and area, is that only for this specific pyramid?
Yes. Yes.
How do we know that?
Huh?
Is that just because it's 4 by 4?
It's a 4 by 4 pyramid. So I'm going to slice it, and every slice I make, it's going to be a square. And its square depends, the length of the square depends on the height that it's at.
No, just for this specific.
It's just for this specific one, yeah. You have to come up with whatever formula is necessary for the problem. Yes?
What's another object where the formula would be necessary? What's another object that you use for this?
You mean where you'd have to do this?
Right.
Anything. Just slice it up and figure out the area.
Yes.
The point is, though, the point is you'd have to be able to figure out the area of the slice. See, in this case, if I slice it, it happened to be a square. If the slice is a messy shape, then we're going to have to come up with some other methods, and we'll learn some of those methods. But so what you want to do is slice it up into something that's easy to work with. Here's another example. Let's find the volume of this thing. Well, I'm going to slice it. What does each slice turn out to be? A circle. And so that basically is the next method, which is called by disc. Our disc method. So, what you do for this method is to find the volume of it. You simply find the volume of each disc and add them up. Let's do an example that's got some more math orientated to it. Example. Find the volume of y equals the square root of x from x equals 0 to 4 revolved about the x-axis. Okay, so the first thing you want to do is get a picture of what you're looking for. So we have a function, y equals the square root of x, which is a half a parabola. So we got half a parabola. We're going out from 0 to 4. So we go from 0 to 4. And then what are we going to do with that curve? We're going to revolve it about the x-axis. So we're going to take this curve, revolve it about the x-axis, so we're going to make a shape that looks like kind of half a coconut.
More like a football.
Okay, half a coconut.
Half a football.
All right. So what we're going to do is essentially slice it, but the slices all are circles, so it's called the disc method. And we're just simply finding the volume of each disc and adding them up. So we basically have discs in here, and we're going to add up all the discs. So volume equals the sum of discs. What is the volume of a disc? It's pi r squared times its thickness. So we need to come up with the volume of each disc by taking the radius, pi r squared, multiplied it by its thickness. So essentially we're going to integrate from 0 to 4 the area of each disc times its thickness. Yes?
Since it has thickness, the 2 points aren't exactly the same, like, as far out, not a perfect circle.
But remember, when we have a thickness here, we have an error. But when we integrate it, what does the thickness become? It's infinitely small. So then the radius, whether no matter which side we use for the radius, it's the same value. Does that answer your question?
Yeah, I was just wondering.
Yeah. Yeah, there's going to be an error. If you just added 20 disks, there would be the error just like there was when we added rectangles. But we're adding an infinite number of disks. All right, so now your task is to figure out what's the formula. Before it was x squared. The formula of a circle or a disk is pi r squared times thickness. Now, you have to determine what's the thickness. Are we going in this direction? Yes. So that means the thickness is a dx. So we want everything in terms of x. So this goes from 0 to 4, pi, this is dx. What is the radius? Square root of x, because the radius is simply the value of the function at that point. And the value of the function at that point is the square root of whatever x is at that point. So we put in the square root of x, and we square. So then the integral becomes 0 to 4 pi times x dx. Pretty simple integral. Which would then be pi x squared over 2, evaluated at 4, 8 pi. So the volume is 8 pi, which is the answer that you should get if you were to use a calculator. Okay, any questions on that one? All right. What's that?
Starting to understand.
Okay, next example, same problem. Find the volume of y equals square root of x from 0 to 4, but revolved about the y-axis. Okay. So the shape is the same. Here we go. The shape is the same, goes from 0 to 4. But now, instead of taking this and revolving it about the x-axis, we're revolving it about the y-axis. So this thing here is going to be revolved this way. So it's not going to look like a coconut, it's going to look like a top.
It's definitely not what I was imagining.
Okay?
Yeah, I'm thinking about like,
I mean, are we still doing this?
Yes, we're still in the disk method.
Out here at this very last place.
Yeah, that's fair.
Okay. Everyone okay with the picture? Because you have to be able to visualize the picture. Even if you can't draw it, you have to be able to visualize it. Because then, once you get the picture visualized, then it's pretty easy. We're still using the disk method. So now what we're doing is we're finding the volume, but we're turning our disk this way, and we're finding the volume of each disk going up in this direction. No, these are disks.
We're still doing this.
are
Okay?
you sure it's not a
Thanks.
So volume equals sum of disks. And so it's going to be an integral. What's the integral going to be? Not from 0 to 4, but 0 to whatever that is.
0 to f of 4.
So if I plug a 4 in here, y is going to be 2. So the integral goes from 0 to 2. Okay? Now, what are we adding? We're adding disks. So disks are pi r squared times thickness. Okay, here's where the change comes in, though, because what is our thickness? Our thickness is now dy, so that means everything has to be in terms of y. So now when you put the radius and square it, the y, it has to be in terms of y. So here's our radius. This radius is x. So x in terms of y would be No, y squared. Because y equals the square root of x can also be written as y squared equals x. So the radius is the x value, and the x value is y squared, so this becomes y squared squared. Okay? Which gives you 0 to 2 pi y to the 4th dy.
Are you supposed to add or multiply those twos?
Multiply what?
The two is the exponents. Raising an exponent.
You multiply. Okay, so this gives you pi y to the 5th over 5, evaluated at 2 and 0. Should be 32 pi 5. Now, that's a different answer than the other one. Why? Completely different shape. The other one was a coconut shape, and this becomes a concave tornado.
No, it's a vortex.
All right.
It's a tornado curve. It's a tornado. It's a vortex tornado.
Yeah. All right.
Like a dome.
Little too talkative today. Try to hold on. Okay. Yeah. The only difference between what we just did and the washer method is that the object has a hole in it. Well, all we're doing is slicing it into a bunch of discs. Each disc has a hole in. So how do you find the volume of the disc? Find the volume of the outside circle, find the volume of the inside circle, and subtract. Okay? So, volume of a washer. It's going to have a little radius and a big radius. So the volume of a washer would be pi big R squared times thickness minus pi little r squared times thickness. We can factor out the pi. We can factor out the thickness. And it leaves you with r squared minus little r squared is the volume of a washer. All right, so let's try an example. We'll create the model with a couple math formulas. Y equals 3x plus 1. Y equals x. Evolved. About x-axis. X equals 0 to 2. All right, what's the picture of y equals 3x plus 1? It's a line, y-intercept of 1, slope of 3. So it's pretty steep. I'm going to make it out here wider. And y equals x is a line that goes 45 degrees. And we're going out as far as 2. So basically, there is the shape that's enclosed. Y equals 3x plus 1 on top. And then y equals x on the bottom from 0 to 2. And then we're taking this and revolving it about the x-axis. So it's revolved about the x-axis. So this part is symmetrical. And this part here goes down there. And it's been revolved, so it's circular. And so it's a, this is revolved here, so it's circular. So it's a megaphone. It's a rah-rah phone for cheerleaders.
I thought of a spaceship.
All right? Can you visualize it? Okay. Okay, so what's the volume? Volume equals the sum of washers. Okay? Which way are the washers going? They're going this way. So that means the thickness is dx. Each washer here looks like that. And it's got a little shape to it. Okay? So we're adding the washers going horizontally. So that means the washers must go from 0 to 2. The volume of a washer is pi times big R squared minus little r squared dx. Okay? Any questions on that? All right, so now you just have to figure out what is big R and what is little r. What's big R? Big R is the radius that goes from here to there, which is the value of y at that point, 3x plus 1. So that's 3x plus 1 squared minus little r is this distance here, and that's just x. So minus x squared dx. Okay, we won't do the integration, but that's the setting up. Most of these problems will be calculator friendly. You just go on the calculator. You won't have to do them analytically, but you need to know how to set them up for the analytical part. All right. Okay. The last method is called the shell method. I call it the tin can.
You know which lot of kids?
All right. Here is a shape that was solved by using washers. The washers were sliced this way, and they came out as washers in the vine. Now, this wasn't sliced very thin, so these washers, there's a lot of air. But it was just to demonstrate, slicing the washers. This one is, you're finding the volume not by slicing it this way, which would give us washers. We're slicing it upside down or vertically, which gives us tin cans or cylindrical shells. So these are each of these, you think of them as a tin can placed inside each other, and it forms the figures. Okay? Well, it's not really a washer though. Okay, a good example would be this. Each of these wraps around are like a tin can, and they just get thinner and thinner and thinner until it can completely enclose the figure. Okay? So, what's the volume of a tin can?
Pi r squared times h.
No, it is not pi r squared times h. A tin can, we're only looking at
The radius times width.
the metal in the tin can. We're not looking for the volume of it because each, you're going to have a whole bunch of tin cans all put in. So all we're looking for is the volume of the metal. So it's the area of the piece of paper that makes the tin can times its thickness. So what's the area? The circumference, because that's what creates the tin can's length, times its height, times its thickness. So the volume of a tin can is equal to 2 times pi times r, which represents the circumference, times its height, times its thickness. Okay, everyone clear on that? Okay. So let's put together an example that does that. Y equals the square root of x. Y equals 4. X-axis. Find volume. If revolved. Okay, y equals the square root of x. We've actually had that one. Y equals 4. I'll wait, I'll wait.
It's all clear.
The x-axis, and find the volume if you're revolved about the y-axis. So we put y equals the square root of x. Then it says y equals 4. So we don't go out here to 4, we go up here to 4. And the x-axis. Here's the x-axis. Here's y equals 4. You know what? Did I copy that wrong? I'm sorry, I did. That wasn't making sense. Sorry. It's x equals 4. Sorry. Didn't think it was. So x equals 4, same as we had before. And the x-axis. So this is the shape that's enclosed, this here. Then we're taking that shape, revolving it around the y-axis. So this thing here gets revolved around this direction, so we have a symmetrical shape over here. And it's circular. Okay. All right. So what we did is we took this, revolved it around, and that created a shape that was just like this. Look at it from the front, that's what it looks like. But then inside, it has a hole that goes down to a point. So it's got a hole inside that's going all the way down to a point. Okay? You could very easily do this one with the washer method. You could just have washers go here. The first washer would be a wide washer with a tiny hole. And then the next washer would be the same size on the outside, but the hole would keep getting bigger. Alright? But what we're going to do is find its volume by using a tin can. We're going to drop a tin can in and then just keep expanding the tin can. So the first tin can is down here. Actually, it's way down here, but okay. Then we put another tin can next to it. And all the way and just keep going until we're all the way out. So those are the tin cans. We start with a little tiny one, going all the way out. So volume equals sum of tin cans. Okay. This gets a little messy, so you gotta make sure you have to keep track of everything. So it's going to be some integral. We'll figure that out in a minute. The volume of a tin can, 2 pi r times height times thickness. 2 pi r times height times thickness. Okay, first thing to establish is the thickness. Our tin cans are going this way. They're not going that way. So the thickness of each tin can has a thickness of dx. Okay? Everything has to be in terms of x then. So this portion is dx. That means our integral must go along the x-axis. Does the integral go from -4 to 4? No. Because where does our first tin can start? Right there at 0. And then where does our last tin can end up? At 4. So the tin cans are created going from 0 to 4. 2 times pi. What's the radius? Well, radius of our tin can is this distance right there, x. The height of our tin can, that's right here. That's a y value, which is the square root of x, because it was created by this function, which is the square root of x. So we replace r with x, that's okay. We replace height with the square root of x. And there's our answer. So we did 0 to 4, 2 times pi, x to the 3/2 dx. Which, all in all, isn't that hard to integrate. Well, what would it be? X to the, well, 1 power higher, 5/2 times 2/5. Evaluate it at 4 and at 0. So we get 4 pi x to the 5/2 over 5. Evaluate at 4 and 0. Plug in a 4. 5/2. Ooh, but you can do that. You can do that. What's 1/2 x 4 to the 1/2? 2. 2 raised to the 5th is 32. So you're basically going 4 times 32 times pi divided by 5 is your answer. Okay. All right, any questions on that? Now you could have used washers, but you need to be skilled in both, because what happens is you use one method and it's going to be a real messy integral, whereas if you use the other method, it becomes can become a much simpler integral. And it especially plays a role if you're doing it in the free response part, where you have to not use a calculator. Yes?
Could you just find the variable that you're subtracting? Like, if you were having this on.
You could find the area of the whole thing, and then the area of the inside. Yeah, because then what you'd be doing is you'd be using the disk method to find the area of the inside, minus the area of the whole thing, which would be just a standard red cylinder. Sure? Okay.
So, what that would actually, like that little thing we have there without the little one, the one here closer to, yeah. So, what is that? Are those getting like, is the hole getting smaller?
The hole's getting smaller.
So that's what that would look
Yeah,
like.
right. It just, I don't have to go all the way to point, but it'd be the hole getting smaller to a point.
Oh.
So you could very easily do it with the washers.
Are there any hints to know whether to use the tin can with the washers, or is it just kind of a guess and check?
Guess and check. And what's going to happen is, in one case, you're going to get an integral like that, and in the other case, something like that. You know, both are doable, but if you had to do it by hand, I'd much rather integrate this than try to integrate that. That would be the difference, the way it gets set up. Christina? Okay, shh, shh, shh. Good question, because it's always confusing. Basically, what you're looking for in the tin can is what's creating the radius. And the thing that's creating the radius is where you start and where you end up. And that's why it goes from 0 to 4 rather than -4 to 4. Because you're basically creating your tin cans. Okay, where does the center of the tin can start? It starts at 0. Where does the tin can end up? It ends up at 4. Okay? Yeah, because it's often confusing. People think, but the tin can didn't start at -4, it started at 0.
But would you be able to do it, because 2 pi r is just the diameter times pi, so would you be able to just like replace it? I know it's somewhat complicated, but would it just be, like, could you do -4 to 4, but it would just be pi times the diameter times height times the thickness?
Yeah, I haven't looked at that. Maybe, The trouble is, yeah, maybe so. The thing that's happening here is this is consistent. And, you know, if this changed, of course, then, I don't know, you might be right. You might be right. You probably are, because all you're doing is changing this to D, which means you're doubling your answer, and then you're doubling it. So as long as it's a symmetrical shape, I think you'll be fine. Okay, any other questions? All right, it's a tricky unit because of the visualization, so we'll be spending the next 3 days working on it, and then the quiz will be Friday, covering sections 7.1 to 7.3. Okay. All right, thanks for joining us. You able to go?